All right, let's talk about chemical kinetics. It's not just about what happens in a reaction, but how fast it happens. We're diving into the science of chemical speed. So, have you ever wondered about this? How can a firework just explode in a split second, but something like an iron ship can take decades to rust? I mean, they're both chemical reactions, right? The secret? The big difference is all about their speed. And that's exactly what chemical kinetics is here to help us understand and measure.
Okay, so if we're going to get a handle on reaction speed, the first thing we've got to do is, well, measure it. And you can think of this like a speedometer, but for chemistry. Let's take a look at how it works.
And here it is, the rate of reaction. It sounds complicated, but it's really just this: how much a chemical's concentration changes over a certain amount of time. The unit we use is moles per liter per second. I know that's a mouthful, but you can basically just think of it as the chemical equivalent of miles per hour.
And what's cool is that we actually have a couple of ways to do this. We can measure the rate by watching how fast our starting ingredients, our reactants A and B, are getting used up. Or we could flip it around and watch how fast our final product, C, is showing up. Either way you track it, you get the same answer, the reaction speed.
Okay, so knowing the speed is one thing. That's super useful. But what actually controls it? What's pulling the levers? For that, we need to dig into the reaction's rulebook, which in chemistry we call the rate law. And this formula right here, this is the rate law. It's really the heart of kinetics. It shows us that the reaction's rate is tied directly to how much of our reactants, A and B, we have. That little k is just a number, the rate constant, that's unique for every reaction. But the real secret sauce, that's hidden in those little exponents, m and n. Now, listen up, because this is probably the single most important rule in all of kinetics. You absolutely cannot just look at the balanced chemical equation and guess what M and N are. No way. You have to figure them out by doing experiments. It's only by actually running the reaction in a lab that you can find out how much of an impact each reactant's concentration really has on the speed. Let's make this real with an example. Take the reaction between nitric oxide and oxygen. When you do the experiments, you find something interesting. The rate depends on the concentration of NO squared, but only on the concentration of O2 to the power of 1. So in chemistry speak, we say the reaction is second order for NO and first order for O2. And the overall order of the whole reaction? Super simple, you just add them up. 2 plus 1 gives you a total order of 3. Okay, so this whole experimental thing brings up a really common point of confusion for a lot of people. It's this gap between what a reaction looks like on paper versus what it does in reality. So let's clear the air and talk about the difference between two really important ideas: order and molecularity. So here's the simplest way to think about it. Molecularity, that's the plan on paper. It's the theoretical number of molecules that are supposed to bump into each other in one step of the reaction. But the order, that's the real-world result. It's what you actually measure in the lab, the real impact that concentration has on the speed. Let's dig a little deeper here. The order, remember, comes from those exponents we found in the lab. It can be a whole number, a fraction, or even zero. But molecularity, that's just a head count of molecules colliding. You can't have half a molecule in a collision, so it's always a whole number. And here's the biggest difference. Order is for the entire overall reaction. Molecularity, though, that's for each individual tiny step that makes up the whole process. All right, so we can measure the speed and we know the rules that govern it. So what's the payoff? Well, this is where it gets really cool. We can basically predict the future. We can calculate exactly how a reaction is going to play out over time, and we do it using a tool called integrated rate equations. It all starts with a super practical question, right? Like, hey, if I start this reaction now, how much of my stuff will be left in 10 minutes? The tool that answers that question is an integrated rate equation. I know, the formula might look a little intimidating at first glance, but its job is actually really simple. For a first-order reaction, this exact equation lets us pinpoint how much stuff is left at any moment in time. Now, one of the most useful ideas that comes out of these equations is the concept of half-life. And you know what? It acts completely differently depending on the reaction's order. So let's have a little showdown. Zero-order versus first-order reactions. So first things first, what even is a half-life? Well, it's pretty much exactly what it sounds like. It's the amount of time it takes for half of your starting material to be used up in the reaction. So if you start with, say, 100 grams of something, the half-life is just the time it takes until you only have 50 grams left.
Okay, showdown time.
For a zero-order reaction, the half-life actually depends on how much you start with, so more stuff means a longer half-life. But for a first-order reaction, the half-life is always constant. And this is a huge deal in the real world. Think about taking an antibiotic. They tell you to take one every 8 hours, right? That's because it's a first-order process. After 8 hours, half the dose is gone, no matter what. So you have to top it up to keep the concentration high enough to fight the infection. It doesn't matter if it's the first dose or the 10th. The time it takes to have is always the same.
So let's step back and see how all these pieces fit together. We've talked about rate, order, and half-life. When you combine them, you get this incredibly powerful toolkit, a kind of blueprint for understanding and even controlling pretty much any chemical reaction. Think about the workflow here. We start with experiments to find the rate law. That rate law gives us the reaction's order, and that order becomes our guide, our blueprint. It tells us, okay, for this reaction, you need to use this specific integrated rate equation. It points us down the exact mathematical path we need to follow to predict how the reaction will play out over time. It all connects. And believe me, this isn't just stuff for a textbook. This entire toolkit is how scientists in the real world design faster-acting medicines, create stronger, more durable materials, and fine-tune massive industrial processes. It gives us an unbelievable amount of control. So that brings me to a final question for you. If you had this power, this chemical blueprint, what one real-world reaction would you want to control? Would you speed something up, like healing, or slow something down, like aging or rust? Something to think about.